Hi everyone, here's your last experiment which is experiment 12, in fact, Lewis dot structure and molecular bonding theories. And this handout we're going to learn how to draw Lewis structures, even though you know how to draw it because we have a homework assignment if you were in the lecture with me, so you may have done that already. And also in the lecture we covered how to draw the Lewis structures, but here you have a handout where you can practice drawing Lewis structures. Okay, and then we also talk about the resonance structure. So the resonance structures are that you can have the same atom placement of the Lewis structure would be the same, but instead the double bonds and the lone pairs can delocalize. That's the resonance structure. So this is the carbonate ion, CO3 2 minus carbonate ion. There are 3 resonance structures. Okay. And then we also talked about formal charges and how to calculate the formal charge. Normally, formal charge is calculated by taking the group number of the atom that we are interested, and then you subtract the number of bonds and number of lone electrons that is attached into that bond in the Lewis structure. That gives us the formal charge. And here's another example of a Lewis structure, CH2F2. And then the VSEPR theory, VSEPR and the valence bond theory. This tells us that how the electron groups arranged in the space to give minimal repulsion between the bonding pairs of electrons or the lone pairs. And also a valence bond theory talks about that when you form a bond, orbitals hybridized to occupy electrons in the bonding orbitals. So that's the valence bond theory. We also learned about hybrid orbitals. And here is a summary of the hybrid orbitals and then the electronic geometry of the molecules. So electron groups could be a single bond, or it could be a double bond, and also it could be a triple bond. So the type of electron groups, it could be a single bond surrounding the central atom, it could be a double bond, it could be a triple bond, or a lone pair, or a lone electron. They are all considered as electron groups. So if you have 2 electron groups, this is the shape that you can see how the way it is drawn, and their hybridization is going to be sp. Okay, and if you have 3 electron groups, hybridization would be sp2. So when you have 2 electron groups, the best way that the 2 groups can be far apart from bumping into each other to minimize the repulsion is the linear electronic geometry. So if you have 2 electron groups, hybridization would be sp and the electronic geometry would be linear, and the ideal bond angle is 180. If you have 3 groups, 3 electron groups, hybridization is sp2, electronic geometry would be trigonal planar, and the ideal bond angle going to be 120 between the atoms. And if you have 4 electron groups, hybridization is sp3, electronic geometry would be tetrahedral, and the bond angle 109.5. When you have 5 electron groups, hybridization sp3d, trigonal bipyramidal electronic geometry, and then we have 2 bond angles 90 and 120. When you have 6 electron groups, hybridization would be sp3d2, octahedral electronic geometry, and ideal bond angle would be 90. Okay, so we have another chart, but prior to that we also need to know how to find out if a molecule is polar or not. you can have some polar bonds. For example, carbon dioxide, the resonance structure is drawn here, and between carbon and oxygen the bond is polar. Bond is polar. You can see oxygen is more polar compared to carbon, so we can draw two polar bonds, wedges, showing that it does have polar bonds, but it's a linear molecule. So the bond polarities get cancelled because the carbon is in the center. The two oxygens on the either side is pulling electron towards itself in the same amount in the opposite direction. So as a result, there won't be a polarity in the molecule as a whole. So there is no net dipole moment in the molecule, and as a result, it's a non-polar. And then if you take hydrogen cyanide, nitrogen is more electronegative compared to carbon. So there is a net dipole towards nitrogen. And between hydrogen and carbon, also carbon more electronegative. So there is a net dipole moment. As a result, the molecule will become polar. Okay. Now after you figure out, depending on the number of electron groups, what is the electronic geometry, and we can figure out the molecular geometry. Normally, if you don't have any lone pairs in your molecule, your electronic geometry and molecular geometry would be the same. But if you do have a lone pair, so then your molecular geometry could be different from your electronic geometry. But the placement of the electron groups would be the same. Okay? Molecular geometry describes the shape of the atoms surrounding a central atom. Essentially, it ignores the lone pairs. The lone pairs are present and do take up space, but they are not visible in terms of molecular geometry. Molecular geometries are listed for electron groups equal to 2 through 6 in table 2. Now, if you have two electron groups, the structure is shown here, BAB. Hybridization SP, electronic geometry would be linear. There are no lone pairs. Molecular geometry also would be linear, ideal bond angle 180. If you have three electron groups, okay, so if you have three electron groups, you can have three atoms surrounding the central atom A. Hybridization, when you have three groups, sp2, and trigonal planar would be the electronic and the molecular geometry, so the bond angle 120. But if you do have three electron groups, but one of them is a lone pair, so the lone pair also do take space, so it comes from the trigonal planar electronic geometry. Okay, trigonal planar electronic geometry, but the shape of the molecule or the molecular geometry would be bent. Okay, it's not going to be linear because you need to have a lone pair, also need to be in the space. So it's a trigonal planar electronic geometry, molecular geometry would be bent. And if you have four electron groups, hybridization would be sp3, and the electronic geometry tetrahedral, molecular geometry also tetrahedral because there are no lone pairs, bond angle 109.5. And if you have a lone pair as one of the electron groups, your hybridization still going to be sp3 because there are four electron groups, and then the electronic geometry would be tetrahedral. Excuse me. Electronic geometry would be tetrahedral, and then the molecular geometry would be trigonal pyramidal. Okay, trigonal pyramidal molecular geometry. Because one of the corners of the tetrahedron, now you have a lone pair, and it's like a pyramid, and then it's a trigonal pyramidal molecular geometry. Electronic geometry would be tetrahedral, and the ideal bond angle going to be, it's going to be less than 109.5 because the lone pair repel bonding pairs more, because lone pair takes up more space. It's going to be less than 109.5. Same thing here, would be less than 120 degrees. And then from the 4 electron group electronic structure, you can also have 2 of them be lone pairs. Okay, so then your hybridization is going to be sp3, since you have 4 electron groups, 2 lone pairs and 2 bonds. And then the electronic geometry would be tetrahedral, but the molecular geometry going to be bent, because the lone pairs also takes up some space. So the molecular geometry would be bent, and the ideal bond angle going to be a little bit less than 109.5. Again, because there are 2 lone pairs, they repel each other. As they repel, so the bond angle between BAB will become smaller than 109.5. Okay. And then the next category would be when you have 5 electron groups. So when you have 5 electron groups, hybridization going to be sp3d, electronic geometry and the molecular geometry would be the same when the 5 electron groups are all bonds. Trigonal bipyramidal, ideal bond angle 120 and 90. So the axial BAB is on the vertical axis, and then you have 3 B's on the horizontal axis. Okay, so there are 2 bond angles 120 and 90. And then if one of these atoms is replaced with a lone pair, so you still have 5 groups, 5 electron groups. So it would be sp3d, hybridization, electronic geometry, trigonal bipyramidal. But now the shape is going to change because you have a 1 lone pair in one place. So it would look like seesaw. Okay, and then the bond angle going to be a little bit less than 120 and 90 due to the repulsion from the lone pair. Normally in a trigonal bipyramidal geometry, if you want to put a lone pair gonna stay in the equatorial position. So the axial bonds are these ones. These are called axial bonds. And then the other 3 are called equatorial bonds. Equatorial bonds. So there the bond angle is about 120 between the equatorial bonds. So because of that, the lone pair normally takes space in the equatorial position. Okay. And then if you have 2 lone pairs out of the 5 electron group arrangement, the 2 lone pairs can take in the space of the equatorial position. So we still have the hybridization sp3d, since there are 5 electron groups. Electronic geometry would be trigonal bipyramidal. Molecular geometry would be T-shape. Right? So it's look like a T over here. And then the ideal bond angle is going to be 90. Ideal bond angle going to be 90. There's no 120. 90, but it's going to be less than 90. Okay. And then the next one, when you have 3 lone pairs out of the 5 electron groups, sp3d going to be your hybridization. Electronic geometry would be trigonal bipyramidal, and then the molecule will become linear now because the 3 lone pairs are going to be on the equatorial position. So the ideal bond angle is going to be 180, not 120 or 90, 180. Okay. And then when you have 6 electron groups, hybridization going to be sp3d2, and electronic and the molecular geometry would be octahedral, and the bond angle is 90. And when you have 1 lone pair out of the 6 electron groups, you still have 6 electron groups, making it hybridization sp3d2, octahedral electronic geometry. So the molecular geometry would be square pyramidal. It's like you have a square, and then on the axial B will make a pyramid, so square pyramidal. And the bond angles are going to be 90. Excuse me. In fact, it could be a little bit less than 90 since the lone pair repels. And then if you have two lone pairs, they're going to be on the opposite of each other, having a square planar molecular geometry, but still the electronic geometry would be octahedral and the bond angles are 90. It's not going to deviate from 90 because it's symmetrical molecule. So that is square planar. Okay, so those are the electronic and molecular geometries. Excuse me. Now with that in mind, what you need to do in this handout, you have to draw the Lewis structure of these molecules and then have to say what is the electron domain geometry by counting the number of electron groups. You find the electron group by counting the number of electron groups, find electronic geometry, and then refer to the molecular geometry by looking at how many lone pairs are available. You can refer to this chart. And then the hybridization, of course, we talk about that. And then you can find out whether you have polar bonds or the polarity get cancelled due to the symmetry of the molecule. If the one polarity does not get cancelled, then the molecule is polar. CH4 is an easy molecule. You